Good evening, everyone. So in the last class, we discussed about some of the properties of electric field lines. And one of the important property of electric field line that we discussed in the last class was about the electric field line is a continuous line, right? The electric field lines are the continuous lines and there are no breaks and the jumps in the electric field lines, right? And it's a pictorial representation of electric field. And the important property of electric field line is that at any point on an electric field line, the tangent at some point on an electric field line gives us the direction of the electric field line, gives us the direction of electric field at that point. Or it also gives us the direction of the force on the positive charge at that point. So let's discuss one of the important properties. One of the important property of electric field line. Suppose we have positive charge. We have positive charge here, and this is the positive charge here. The electric field lines due to positive charge, isolated positive charge. We also studied about the electric field lines due to isolated positive charge, isolated negative charge in the previous lectures also. These are the straight lines away from this charge. These are the straight lines away from this charge, spherically symmetrical and radially outwards. So these are the electric field lines due to a positive isolated charge. So these are the electric field lines due to a positive isolated charge, right? And because of the negative charge, if this is once again a negative isolated charge, isolated means there is no other charge in the vicinity of this charge. Then the electric field lines, because of this negative charge, are going to terminate on this. They are going to terminate on this. So this is how the electric field lines are directed towards the negative charge. So important point is that electric field lines originate from positive charge and terminate on the negative charge. They originate from the positive charge and terminate on the negative charge if the two charges are in the vicinity. If the two charges are not in the vicinity, if there is an isolated positive charge or isolated negative charge, then the electric field lines from the positive charge originate from the positive charge and terminate at infinity. So these electric field lines, because of this isolated positive charge, will terminate at infinity, right? And because of this negative charge, the electric field lines will be terminating on this negative charge from infinity, right? The next property is that electric field lines gives us the measure of a charge. The electric field lines gives us the measure of the charge. Let's suppose this is the charge Q1. This is the charge Q1, and this is the once again one more charge Q2. Electric field line as a measure of charge means that more the number of electric field lines originating from a positive charge or terminating on a negative charge means that the charge is having the more magnitude, right? The charge is having the more magnitude. Suppose this positive charge, on this positive charge, these are the electric field lines originating from this positive charge, right? These electric field lines are radially outwards and originating from this positive charge, correct? And we have another charge here. The electric field lines are originating from this charge Q2. It's an isolated charge. But here the density of electric field lines originating from this positive charge is more. The density of electric field lines originating from this positive charge is more. So it means that more the electric field lines originating from a charge or terminating on the charge, it means that the charge is having greater magnitude. So it means that the magnitude of a charge is directly proportional to the number of electric field lines. Number of electric field lines. So more the number of electric field lines, more will be the magnitude of charge. So we have two cases here. In the case one, this is our case one. This is our case one, and this is our case two. Case A and case B. In the case A, the number of electric field lines originating are less as compared to the number of electric field lines originating from the case P. So we can say that the magnitude of charge Q2 is greater than the magnitude of charge Q1. So electric field lines gives us an idea about of the magnitude of a charge. So greater the electric field lines on a charge, greater will be the magnitude of that charge. So this is one of the important properties of electric field lines. So in this question, we have two charges Q1 and Q2. We can see here that we have to identify which charge Q1, which charge is having the greater magnitude, Q1 or Q2. We can see that from Q1, the number of electric field lines, if we see in the Q here in this case, we can see there are 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 electric field lines are originating from this charge Q1, and only 1, 2, 3, 4, 5, 6, 7. Only 7 electric field lines are terminating on the charge Q2. You can see that 9 electric field lines are originating from charge Q1 and only 7 electric field lines are terminating on the charge Q2. It means that the charge Q1 is having a greater magnitude as compared to the charge Q2. So from here we can conclude that mod of Q1 is going to be greater than mod of Q2. So our option 1 is going to be correct. And one more point is that since charges are electric field lines are originating from Q1 and they are terminating on Q2, it means that this Q1 has to be positive. This Q1 charge has to be positive and this Q2 charge has to be negative, right? So Q1 charge electric field lines are originating from Q1 charge and electric field lines are terminating on the Q2 charge. We know that electric field lines originate from positive charge and they terminate on negative charge. It means that Q1 must be positive and Q2 must be negative. So two options will be correct in this case. So option 1 and the option 3 are the correct options. Let's move on to the next property. The strength of electric field is measured by the line density. It means that more the density of the electric field lines at some point, more will be the strength of electric field at that point. Let's suppose that these are the electric field lines here. In the case 1, these are the electric field lines here. Let me call this as EA. And the case second, case B, these are the electric field lines. We can see that in the same area, the electric field lines are more in the case second than in case first. So we can see that the number density of electric field line gives us the measure of electric field strength at a point. Here the number density is less. Number density here means the number of electric field lines in a particular region here. Number density is less. And let's suppose the electric field strength here is AB, but number density here is more. In this case, the number density is more. So it means that electric field at B is going to be greater than electric field than A. It means that the field at B will be greater than the field at A because the number density of the electric field lines at in case second is greater than the number density of electric field lines in case 1. Let's discuss another case. Let's suppose that these are the electric field lines. These are the electric field lines here. Let me call the electric field at this point as EA and electric field at this point as AB. So this is the direction of the electric field lines. We cannot intersect these two lines. So the two electric field lines cannot intersect each other, but we can see that in this region here, in this region, and if we compare this region and this region, let me call this region 1 R1 and let me call this as region 2, that's R2. In this case, number density is less, right? You can clearly see that number density is less. And once again here, the number density of the electric field lines is more. Number density of field lines is more. So if the number density of electric field lines at region 1 in region 1 and the number density of the electric field lines in region 2, so in region 1 the electric field lines are more, density of electric field lines is more, we can clearly see that the electric field strength at in region 1 will be greater than the electric field strength at region 2, because the number density at region 1 is greater than the number density at region 2. So this is one of the important, once again, another property of the electric field lines. It gives us idea about the how the electric field intensity is going to vary in different regions. It depends upon the density of the electric field lines in different regions. Greater the density of electric field line at some point, the greater will be the magnitude of the electric field at that point. And the direction of the electric field intensity at a point will be given by the tangent drawn on the electric field line at that point. Electric field lines due to static charge do not form closed loop. This is a very important property, that electric field lines due to static charge, if you have static charge, they never form a closed loop. It means that, suppose that we have a charge Q here, plus Q charge here, and these are the electric field lines due to this plus Q charge. And they are originating from this plus Q charge and they are radially outwards, straight lines radially outwards. And these electric field lines are going to terminate at infinity. These electric lines are going to terminate at infinity. These electric field lines are going to terminate at infinity. So they will never form a closed loop, because we know that electrostatic field, because of the static charge, it's a conservative field. It's a conservative field. It's a conservative field. Electric field due to static charge, it's a conservative field. And we know that if in case, if we suppose that the electric field due to these charges form a closed loop, then in that case, the electric field will not be a conservative field, because in that case, the work done in the closed loop in this field will not be equal to 0. So it has to be, since it is conservative, so work done has to be 0 in this case. In this case, that electrostatic field, because of this plus Q charge, these are the conservative fields. And if they form the closed loop, then they will no longer be the conservative fields, and the work done in a closed loop will not be 0. So electric field lines will never form a closed loop. They will never form a closed loop. Similarly, if we have plus Q charge and minus Q charge here, the electric field lines will originate from the plus Q charge and they will terminate on the negative charge. So they will not be forming a closed loop like in magnetic field. In magnetic field, the magnetic field lines do form the closed loop, but here in case of electrostatic field, the electric field line do not form the closed loop if the field is because of the static charge. If the field is because of the static charge, but if the field is because of the varying magnetic field, because of the magnetic field, if the electric field is induced like in electromagnetic induction, the electric field is induced in the conductors, that electric field is not a conservative field, and that field do form the closed loops. That's not at all a conservative field. So electric field lines are going to terminate on the negative charge. So this is the important property, that electric field lines will never form a closed loop. they will never form a closed loop. Reason being that it's a conservative field. If it forms a closed loop, then the work done in a closed path will never be equal to zero, right? Because electrostatic field, electrostatic field, you can write the reason here. Electrostatic field is a conservative field and work done over a closed path is equal to zero. So this is the reason that electrostatic fields due to these static charges will never form a closed loop. And one more important property of electric field lines in case of conductors. If we have a conductor like metals, the electric field lines inside the conductor are always zero. There are no electric field lines that exist inside the conductor. It means that electric field inside the conductor is always going to be equal to zero. Let's suppose that this is the conductor area. This is the conductor area. This is the conductor here. And these are the electric field lines. These are the electric field lines on this conductor. Let's suppose this region is the positively charged region of this conductor, and this will be the negatively charged region of this conductor. So the electric field will never penetrate inside the conductor. It will always terminate on the conductor, but it will never uh, exist inside the conductor. So the electric field lines here will terminate on the conductor here. Uh, Electric field lines will terminate on this conductor. Let's suppose this is the conductor here. Just a minute. And let's suppose this is the conductor here. It's a metallic conductor. So the electric field lines will always terminate on this conductor like this. And let's suppose that this is the negative charge here. This region is negatively charged. and this region is positively charged, and this side of this conductor is positively charged. So electric field lines, because of this positive charge, it will originate from this conductor like this, and these electric field lines will never intersect inside the conductor, or we can say that electric field lines will never exist inside the conductor. So these field lines do not exist inside the conductor. And let's suppose that if we have positively charged conductor or sphere here, this is the positively charged sphere here. The charge on this sphere is positive and it is uniformly distributed. It's an isolated sphere. There is no charge in the vicinity of this sphere. The electric field lines because of this sphere will be radially outwards like this, and there will be no electric field lines inside this metallic sphere. It's a conducting sphere, right? It's a conducting sphere. So there will be no electric field inside this conducting sphere. And let's take one more example. Like if we have a negatively charged sphere, we have a negatively charged sphere. The charge on this sphere is negative. Let's suppose the radius of this sphere is r, and this charge, negative charge, is uniformly distributed on the surface of the sphere, and the electric field lines will be like this. It will be terminating, these field lines will be terminating on the surface of the sphere. They will be terminating on the surface of the sphere, and there will be no electric field lines that will be penetrating inside this sphere. So we can say that electric field inside this sphere is going to be zero. In this region, it's once again going to be zero. So this is how the electric field lines behave on the surface of a conductor. So there will be no electric field lines inside the surface of a conductor, or we can say that electric field inside the conductor is equal to zero. Now, in case of dielectrics, suppose we have insulators or the dielectrics. Let's suppose that this is the dielectric placed here. This is the dielectric, right? And let's suppose this is the electric field, and we call this electric field as external electric field. This is the E, and this field is external, right? This field is external electric field. And because of the polarization of this dielectric slab here, this side will become slightly negative charged because of the external electric field, and this side is going to be slightly positively charged because of the law of conservation of charge, because the net charge initially on this dielectric was zero. So if there is a induced negative charge on the left hand side, then there must be same amount of positive charge on the right hand side, right? So this is the external electric field. So because of the induced electric field, because of the induced charge on this dielectric, there will be the internal electric field because of this induced charge. We call this electric field as induced electric field. And this electric field is induced because of the presence of this external electric field, right? Let me call this as E induced. This is the E induced and this is the E external. So the net electric field inside this dielectric, it's going to be, we can see that the external electric field and the internal electric field, due to the induced charge inside this dielectric, they are opposite in direction. So the net electric field will be nothing. It will be E minus E induced. So we can see that E net is less than the E external. It means that electric field does exist inside the dielectric, and this electric field is less than the external electric field. So in case of conductors, we saw that there is no electric field line existing inside the conductor. So the electric field line inside the conductor is zero. But in case of dielectrics, there exists electric field and electric field lines as well, right? So we can see that because of the induced electric field inside the dielectric, the net electric field because of the induced electric field decrease inside the dielectric as compared to the external electric field. So in case of dielectrics, electric field does exist, but in case of conductors, no electric field lines exist inside the conductor, right? And one more important property about the electric field lines are related to the conductors or the metallic surfaces, that electric field lines on the metallic surface always terminate or originate from the metallic surfaces, and they always fall normal to the metal surface. So we can say that electric field lines on the surface of a metal, this is the metal, electric field lines on the surface of a metal are perpendicular to it. Electric field lines on the surface of a metal are perpendicular to it, are perpendicular to the surface. Suppose that there is some external electric field on this, this is a conductor, or we can say this is a metal. And let's suppose there is some, this metallic surface is positively charged, and this is an isolated conductor, right? It means that there is no charge in the vicinity of this conductor. This is a positively charged conductor. If this is a positively charged conductor, the electric field lines will originate from this conductor and they will go to infinity, terminate at infinity. But these electric field lines are going to be normal to the surface or perpendicular to the surface at every point. So they will be like this, and at this point it will be normal, will be like this. And the reason being that we know that metallic surfaces are the equipotential surfaces, and the potential at every point on this metallic surface are same. So there should exist no electric field parallel to the surface of this conductor. There should exist no component of electric field parallel to the surface of this conductor. That's the reason these metallic surfaces are called as equipotential surfaces, because if there is zero potential difference between the two points in a space, if there is zero potential difference between the 2 points in a space, then the electric field in that region will be equal to 0. That will be studying later on, but at this time, if we draw the electric field lines on the metal surface, we have to draw them normal to this surface. So this is how the electric field lines will be drawn on the metallic surface. Let's suppose that we have a sphere here. This is the sphere, and suppose that this sphere is positively charged. This is a positively charged sphere here. So this is how the electric field lines are going to be on this positively charged sphere. They are going to fall normal to this sphere. They will be always normal to this sphere. So these electric field lines are going to be normal to this surface of this conductor. Now let's try to see the electric field lines to different charge distribution. Let's suppose that We know that due to plus Q charge, we know the electric field lines are straight lines like this, spherically symmetrical, radially upwards. And we also know that due to negative charge, the electric field lines terminate on the negative charge like this. These are also spherically symmetrical and radially inverse. So these are radially inward electric field lines. But let's suppose that we have two charges, plus Q and minus Q. We have two charges plus Q and minus Q. We have two charges plus Q and minus Q. So the electric field lines will originate from plus Q charge and terminate on this minus Q charge. And this is how the electric field lines, because of these pair of charges plus Q and minus Q, are going to be like. And they will terminate on this negative charge. The number of electric field lines terminating on the negative charge or the number of electric field lines originating from this positive charge, it depends upon the charge Q. It depends upon the charge Q. So greater the charge Q, greater the value of charge Q, more number of electric field lines will be originating from this plus Q charge, and the more number of electric field lines will be terminating on this negative charge if the charge Q has greater magnitude, right? So this is how the electric field lines are going to be. So in this case, we can see that all the electric field lines originating from plus Q charge are terminating on the minus Q charge. We can say that the magnitude of the plus Q is equal to the magnitude of minus Q charge, right? Similarly, if we have two positive charges like this, we have plus Q and plus Q. We know that the two charges repel, two like charges repel each other. So their electric field lines will be in such a way that the electric field lines also repel each other. So electric field lines, electric field because of this plus Q charge will be like this. They will be repelling electric field lines. So this is how the electric field lines are going to be because of pair of two positive charges. And similarly, if we have the pair of two negative charges, the electric field lines will be just terminating on the negative charge and the behavior of the electric field lines will be similar. Now let's suppose we have a conductor here. Let's suppose we have a conductor here. This is the conductor. And this conductor is uncharged. Uncharged conductor. And inside this conductor, we are placing a charge of plus Q inside this conductor. If you place a charge plus Q inside this conductor, what is going to happen? This plus Q charge will be inducing a negative charge on the inside surface of this conductor. So this will induce a negative charge. And because if the negative charge is induced in the inner surface of this conductor, then the equal amount of the positive charge will be induced outside the surface of this conductor like this. So outside surface will be positively charged and the inside surface will be negatively charged. And we have placed a charge Q at the center of this conductor. So now in this case, the electric field lines inside the conductor will not be zero because we have placed a charge here, right? There will exist an electric field because of this charge. And because of this charge, we know that electric field lines are going to be, this because of this positive charge, the electric field lines will terminate on this charge like this. They will terminate on this negative charge. and they will be normal to this metallic surface. So this will be the electric field line because of this system. And because of this positive charge, the electric field will be radially outwards. And it will be normal to this surface. So these are the electric field lines because of this system. If you place a charge inside this conductor, so this is how the electric field lines are going to be because of this system. And suppose if the similar situation is there, but there is a slight variation in this situation. Let's suppose that this is once again an uncharged conductor, but the plus Q charge is somewhere placed here. It's not symmetrical, right? Here it was symmetrically placed. Now it is asymmetrical here. Once again, it's going to induce negative charge. It's going to induce negative charge on the inside surface. And there will be a positive charge on the outside surface of this conductor. So this will be the positive charge. And this is the charge Q here. So because of this charge Q, plus Q present here, and the negative charge here, there will be once again electric field lines, but these electric field lines have to fall normal to this conducting surface like this. So this is how the electric field lines will be because of this charge. And because of this positive charge, it will be once again a electric field lines, straight lines perpendicular to this conducting surface. So these are the electric field lines. So that's it. In this lecture, we discussed about the properties of the electric field lines, and we also tried to draw the electric field lines due to different charging system, charge system or uncharged system. And we also try to learn about different properties of the electric field lines and apply all those properties in different questions. Let's try to discuss few questions related to these property quickly, and then we'll be discussing electric flux in the next class. The question is that which of the field line pattern is correct for a metallic shell? In this case, we have four patterns given in this question: pattern 1, pattern 2, and pattern 3, and pattern 4. So we can clearly, we know that on the metallic shell, the electric field lines inside the surface does not exist, right? There will be no electric field lines inside the metal, right? So the option number 3 is incorrect. So it's not a possible electric field line, right? Because no electric field line exists inside a metallic conductor. So this is also not possible. And the second important property is that electric field lines on a conducting surface or a metallic shell always fall perpendicular to the surface. So here the only line which falls perpendicular to the surface is line number 4. So it means that fourth line electric field line is the correct electric field line for this particular case. So in this figure shows some of the electric field lines corresponding to an electric field. The figure suggests we have been given a figure here, right? These are the electric field lines, and we have to see which at which point the electric field strength is more, and at which point the electric field strength is less. So we have to give the order of the electric field line at A, B, and C. So we have to give the order of electric field lines at A, B, and C. So we can see that the density of electric field line here is more, and the density of electric field line here is once again more, but the density of electric field lines here is less. And we can also see the density at A is same as the density at C. We can see that it means that electric field at A will be equal to at electric field at C, and this electric field is going to be greater than electric field at B because of the lesser line density at point B. So the option number 3 is going to be correct for this particular question. And this is the last question. A charged particle is free to move in an electric field. It will travel always along a line of force. Along a line of force if its initial velocity is 0. Let's suppose that this is the line of force here, right? Suppose that the charged particle was initially moving in this direction, right? And the let's suppose the electric field at this point is in this direction. And this is the charge Q, positively charged Q. And this charge q was initially moving at this in this direction at an angle of theta with this force because of this electric field. So this charge particle is going to follow this path, right? This charge particle is going to follow this path. It will not follow the path of electric line force. So it means that it will follow the electric path of electric line force only when there is zero initial velocity to this charge particle. So the option number 2 is that correct answer. So let's stop it here, and we'll be discussing in the next class electric flux, and then we'll be discussing about the Gauss law as well. So let's stop here and take care and goodbye.